Okay. This thing still on? All right. Okay. So let's plan this out.
He's in the
What?
elevator. Buff's doing a live stream.
Who's this?
This is great. Okay, so Shia LaBeouf is at Oxford University doing a live stream where he just rides the elevator with people at Oxford.
Just randomly.
Yeah.
And I get
for an art collective that he is.
But do they know that he's there, or they just have to bump into some?
Back in the elevator right now with like.
Right, but do they recognize him at first?
Yeah. No, like this is the experience. You get to ride in the elevator.
Oh, so he's just chilling in the elevator, and people are like waiting in line to get in the elevator with him.
Exactly, and ride the elevator with him.
Man,
I should being live streamed on YouTube.
I should do that in the pharmacy building. We could set up like a sign and everything like that. Like there's somebody like famous. I should just go chill in the library and eat like Starburst.
Wait. If too many people got in there, though, wouldn't the overload sensor?
No, because it's hydraulic over there.
Oh.
Yeah, it's not cable driven.
Okay.
It's fine. The real question is, why do I know that? Okay.
I think you know that.
All right, so let's design this out here. This shouldn't have been that bad.
Well, let's see. I would love to be proven wrong.
This is just cowards.
So now you're gonna do it without the enterprise communication, right?
Correct. I'm gonna do it the way I expected you guys to do it.
All right.
I'm not sure. We had to explain to you, like, it wasn't completely public knowledge as to the benefits of riding in an elevator with Shia LaBeouf. So.
Why is that? Why are there benefits of that?
I don't know. He's watching it. You tell him.
I stopped watching. I get too jealous. I wish I was in the elevator.
Isn't he kind of like a lunatic?
He's amazing.
No, I don't. I have nothing against him. I like him in his movies.
He's not like a lunatic. He's just like he's the kind of like famous where like he can like he does like joke stuff, but he's not like serious about any of it.
Oh, see, I think I've seen some things, like read some stuff where he's kind of like unstable.
Like after
they call it eccentric because you're rich.
After
you're a lunatic, you're poor, you're
eccentric.
eccentric.
Without caring what people thought.
Yeah.
So.
I've never seen anything that like made me thought that he's like genuinely crazy or anything.
Oh, okay.
Like he does like crazy stuff, but like same stuff I'd be doing if I had $1 million, you know.
I get it.
Making music videos.
All right. So
Yes.
here's the deal. All right. So we have an array. So last time we filled up an array, I think with zeros and ones, right? So whether you kept it as zeros and ones, you put in another, it shouldn't matter. All right. So going about this with a normal merge sort algorithm, what does that look like? We look at this and we say, is this trivially sorted? We say no. Why? Because it's not a one list. Right? That's when we know that's how we know a list is sorted by definition in merge sort. So what do? In traditional merge sort, we divide our data in half, and we recursively call merge sort on the left, followed by recursively call merge sort on the right. Now, a downside to this in traditional programming is this merge sort call to the right-hand side has to wait. It doesn't get called until the left-hand side is completely finished. Rather than making recursive calls, what I want to do is I want to have a child process do this, and another child process do this. Handle these. So we're spawning off kind of a boss, if you will, because we see right away we're going to need to have additional child processes doing things, right? So right off the bat, we split this. So we have, and let's leave remnants behind. All right. So this is the parent that's still sitting up here after it just spawned off 2 children. Fair enough? So this is our picture we're drawing. All right. Now, this child says, am I trivially sorted? The answer is no. So this child forks off 2 children. Who each do this, leaving this child here. Now, at the exact same time, or within CPU scheduling time, right? This child over here says, am I trivially sorted? No. So it spawns off 2 additional ones right here. So we have a child here, a child here, a child here, a child here. Let's just drop this down. And then these split into 2 children. Okay, so this is essentially what's happened. All right, is our original flow. So original parent, this is the original parent from our very first start. This guy spawns off 2 children. Each of those children spawns off 2 children. These 2 children are going to be able to finish, and we'll talk about that in a second. See, I heard it while I was coming. You people are sick.
You heard it while it was coming out.
It
The
was-
children were finishing.
It's like a meta phrase.
All right, so. Yeah. Okay, so in any case. So in any case. But this child process is able, has to spawn off 2 child processes who are each now, they decide, my list is trivially sorted. Make sense? So we need to think about, what do each of these children get? So we have to think about the type of information that they need, because they're all dealing with, theoretically, the same list, right? Okay, but what did we see as you started getting into this work? When we create our original list, or create our original array, and then we spawn off in our original one, we'll see it in a minute, we spawn off a single child process. Does he get that original array? Well, he gets it, but it's not the same memory location, right? If we make changes to it, are those changes seen by the parent? No, they're not seen by the parent. That's problematic, right? Hey, go ahead, you had a question?
No,
Oh, you guys figured it out? Now that you realize the assignment's easy?
yeah, I mean, you said to pass the pointer, don't you?
Well,
Not that, I mean, that.
you have to find a way to get to the pointer. Yeah, so the way to do that, which we didn't introduce yet, so this isn't going to be how I solve it, would be with shared memory. You would have a static variable that uses shared memory, and then everybody's it's basically POSIX's version of a singleton. But we're not going to do it that way. All we know about is files and forking.
You showed us the types, so we can use technical types.
Yeah, well, I think I said it to a couple people yesterday. You guys are seniors now, so if you want to research and do something out of the ordinary, I'm fine with that. Okay? I am fine with that. Okay? But my intention is for you to solve it in terms of what we've introduced in class. Because the purpose of the assignment is to bump you into this problem of, why do we need interprocess communication? Because for the first time in your computer science career, really, we have real processes that really need to communicate, and we're seeing that this is really a problem. Right? We have no direct way for these guys to talk to each other. Well, we almost have no direct way for these guys to talk to each other. What we do have is we have files. And we can certainly name files something related to the process ID of the children, so the parent can know about what's happened under the hood.
That's stupid.
So we'll tangle with this. So
Wait, but does the parent know it's child's ID?
the parent gets the process ID of the child. So if a parent calls fork twice, it would get the PIDs of both children. Now the parent could then use those PIDs as if it assumes that a child is going to create a file. Okay. Well, if all of the different processes, we'll just kind of talk big picture then. If all the different processes are all writing to a file, and they preface each line with their process ID, and the parent is interested in that particular piece of information. So for instance, this parent right here knows the process ID of this guy and the process ID of this guy. So both of these guys say, my list is trivially sorted. I'm dealing with the begin and end of just this one part of the list. All right? If that's the case, this guy is going to write some information to a file.
So if the parent stores both the child IDs, how do you access those?
What do you mean, how do you access those?
Like, is there a function or something to access what the child IDs are?
It's sitting in a variable called PID.
In the parent.
In the parent. Yeah, right here. Where is it? Oh, yeah, this guy. When we called fork, the process ID of the child comes back to the parent.
Okay.
Go ahead.
So, getting back to the, So, problem that I ran into is how do you go through the list and split it up without doing it recursively? Like, how are you going to go through that list, split it up, see if they're sorted or not, and if they're not, continue?
Okay.
How are you?
So our original list here had two variables, right? So, well, we had a list of what, 5 things? So let's just put those variables up top here. So from this guy's perspective, begin is equal to 0. Oh, I'll put it in the same. End is equal to 4. Let's just say that's the case for that parent. The original parent creates the array, fills it up with random stuff, sets begin and end to the first legal bucket, the last legal bucket, and says these are my variables. When it spawns off a child, each of these children get their own copy of these variables, right? Whoa, hello. Now this child needs to know that he's dealing with the left half of the list. So however you're going to do the math on the left half. So this guy needs to update his the end to another value. This guy needs to update the end to another value. Now, how does this guy know that he's the left child? The parent's going to call fork twice, right? Whoever's created first. So the parent's going to call fork. So what exists? So this guy doesn't exist yet. So put him off the side of the screen for a minute. Parent calls fork. The parent then asks the question. Well, then we ask the question: am I the parent or the child? If the PID is equal to 0, that means I'm the child. I'm the new guy, right? So inside of that, if he's the new guy, then what's going to happen? He's going to artificially just decide end is n divided by 2. Say that's the case, right? For the first grouping of the first if statement. If I'm the child, divide n by 2. Else, I must be the parent. What does the parent then do? Forks again. Inside of that, the next question says, oh, if I'm the child, what do I do? I update begin. So this is a second if statement inside of the else of the original if statement. So this guy will say end minus begin, what is it? Begin plus n divided by 2. Is that the right math for it? Yeah, we'll have to think about the math. I think that's the right math. But in any case, this will mean we start at 3 and end at 4. I think it's begin plus n divided by 2 plus 1. I think that gets us to the beginning of the second half of the list.
Divided by 2 plus n mod 2.
Yeah, that makes sense because that's if it's even or odd. Then
Yeah.
That's the
Well, no, but that's only if you're trying to divide it evenly every single time. As long as you
No, because
consistently.
otherwise you won't get the.
yeah. You'll
Well, I
miss-
suppose if you just do it that way and do it consistently, then it'll just be.
Yeah.
You can just divide 2 and give uneven half of the list.
If you always give the left-hand side the uneven half of the list, then you're fine. Realistically, you as long as you're always dealing with half of the list and the guy, you don't leave any buckets behind,
Yeah.
and each process knows that he's sorting within his little world, then we're fine. Okay, so these two children were created. This one was created first, and since he was created first, he knew that he had to change the end. Since this one was created second, he knew he had to change begin. Make sense? Same thing happens again over here. So when we go to the left-hand side, we're going to say 0 to 1. So we're updating these variables. Okay, we already have a copy of these variables. We only had to define the variable once, those two variables one time, originally in the original parent. And then every child gets a copy of those, and they're not linked to the original. It's their own version of that memory. It's a duplicate of that process, right? So we can update begin and end. So this guy will be 0 to 1 for this guy. And this guy will be 1 to 1. Actually, no, this will be, this was 0 to 2. When we split it to the left, this is 0 to 1. And then it should be 2 to 2. Okay, that guy's 2 to 2. All right, and we know, well, we'll come back to that in a second. So then this guy down here should be 0 to 0. And this guy here should be 1 to 1. Whatever. Let's just roll with this for right now. All right, so when we get down here, both of these guys have decided I'm done sorting because they are trivially sorted, right? None of these other guys have done any work yet except forked children. It's the only work they've done, Abe. Okay. I heard that. All right. All right, so in any case, this guy decides, okay, well, I have nothing special to do because my list is sorted. I have nothing special to do. My list is sorted. So both of these guys can die. These children can, they were unwanted children. We thought we needed them, but we didn't actually need them, almost. Because in this particular world, we have an issue. These two children need to somehow make their parent aware that they have finished sorting their list, even though we know, looking in, that each of those children really didn't do any work. They just happened to get an already sorted list. That was a one list, right? All right, so now we have to ask the question. This is the problem that we stumble on. How does this child communicate to his parent that that he is done with his work using only what we've introduced in class, which is the intent?
The audio for this class could like double as family psychology.
Like, I don't know, but do I get like a tissue or a hug or something? Remember that from, was that the movie Armageddon? Remember Armageddon? Did you see the movie Armageddon? The big black guy was in Green Mile. Did he die this last year? I think he died recently. Well, whatever it was. Well, like the NASA was like interviewing these guys, right, to see if they were like fit for space. They found like horse tranquilizers in this guy, and they were everybody was gonna fail. These guys had like major psychology problems, and it shows this giant dude in the room just crying. It's like, do I get like a hug or something with this? My favorite part was the Steve Buscemi one where they get off the nuclear warhead. So, I just wanted to feel the power between my legs. Recorded Christian worldview. All right. So we need to have a way for this dude to communicate to his parent that he's finished his job. How does he do that? And in our context, using only what we've discussed in class. The hint is file I/O, right? We haven't done that much, so we know file I/O, so we can write stuff to a file. We kind of know this other stuff exists, shared memory and stuff like that, and we certainly can guess that's where things are going. But if we only had access to a file, all right? If I just got this one list, and I'm like, okay, my job is done, okay? And my parent here is Nick, and I need to make him aware, okay? But we are locked in different cells, okay?
You'd be locked in the same cell.
No, if we were in the same cell, we wouldn't have a problem here. We'd have a shared variable.
Where we output to a file the process ID, just the process ID, and then once the parent sees that both of its children's process IDs have shown up in this file, it knows that its children are done, so it can start to do its thing.
Okay, so this parent here, see, Nick here is a very concerned parent.
That's exactly how I would describe him.
Okay. Well, we're in different cells, so this is.
No.
Dude, what happened in Vegas?
Okay.
No.
All right. Shut up.
Goat
Shut up.
Carried the ring.
All right. So in any case, he's going to continue to sit there and read a file, looking for the process ID of one of his, well, at the end of the day, both of his children, right? How many of my children have finished their task? So as soon as I have written to the file as this child, okay, saying that I'm done, now I can go ahead and the parent can now move forward. But here's the problem. Does the child know their, do they know their process ID? The parent knows the process ID of the child. But does the child know their own process ID?
PID, right?
The child's process ID, the child's PID is equal to what?
Yeah, but you can call
So-
the get PID function and it should return the
Fair enough. Fair enough. A child can certainly, a process could request
Yeah.
its PID, but I'm assuming we didn't have that, which is fair. I mean, you could use it. Okay, this is the MacGyver solution we're dealing with. Only what we had available to us. The parent knows about its child process IDs, but from the child's perspective, he's a big zero. That's all he knows. Like, okay, well, at the very least, I know that I'm not somebody else's parent yet, right? Because some funny business is about to go down. Certainly when we're up in this area here. All right, so wait, I think we might need some adult supervision. All right, so in any case, so if I'm the child and I have finished my sorting and I need to let the parent know, we can have, so the worried parent here, Nick, can be sitting here reading through a file over and over and over again. Are the children done? Are the children done? Are the children done? Over and over again. How does he find out that the children are done?
Meet thermometer.
Child dies.
Oh, okay. Well, so now we're somebody here, gunshot. Okay. So again, we're thinking about interprocess communication stuff. We're all these questions I'm asking in here in context of what we've done in class.
Couldn't we just write 2 zeros in the file, and it would know that its children are done? Because
Well, keep in mind you have other parents above.
Yeah,
So this second row here, I mean, you're these guys' parent. So how do you, are you gonna get confused? Are you gonna think one of your zeros is done when it's actually this zero that's, you see what I'm saying? Yeah, we can't just have a whole bunch of zeros. And I have no way of uniquely identifying myself by the by a process ID, as far as we know.
Create a count.
Oh, that would be handy. Very handy.
Count, so each time it goes through it, it would add 1 to it.
But how does that?
So we start off with a child number variable all the way up here.
0. And then each time you spawn a child, you add 1 to it, so that
Child number, this is equal to 0.
How does that help you identify that child unless you tell that child what its number is?
Child's going to find out what his number is at. You don't have to tell him. Child gets a copy of that variable.
Wow, that's pretty smart.
Okay, child gets a copy of that variable. And it's his own copy, so he doesn't have to worry about anybody else modifying it, right?
But what happens when you spawn your first child, increment the child count, spawn your second child?
No, you're going to increment it first. Okay, so I'm the original parent.
Okay.
Okay, I'm the original parent. And I'm going to, well, actually, it doesn't matter if you increment it first or not.
Okay.
So
My point is, what happens when those children start spawning children? Because then they both have a copy of the variable.
He's right. They both have a
But-
copy of the one variable, so now their kids are gonna both have a copy of the two variable.
No.
Yeah.
because
No, the first child will get child 1.
in the
Second
second
child
one,
will
yeah,
child
it'll
2.
be a two.
he's thinking there's going to be 2 2s.
Yeah, but it's not. It's gonna
The
be 2
first-
3, but there will be another 2 3 over on this side.
The first child, the child number 1 is going to get 2. And so you're going to have two
So you'll have the first grandchild
Yes.
in your thing will have an equivalent unique number, equivalent child number as the second original child.
Yes.
Okay, using just that math. We haven't talked about how we're adding to it yet. Okay, but you're right. So if I only increment by 1, you're right. So let's think how we can increment. Again, we're playing MacGyver here, right? So we'll just start at the top. The original parent says, I have no children. Parent decides my list is not sorted. I'm going to spawn off child 1. Boom, child 1 has been forked. All right. Child 1 becomes aware that he is child number 0. Whether I incremented it first or not, we'll just use the 0 as our example. Okay, so I'm child 1 in this example. My number is 0. Okay? And so I'm off doing my thing now. I because I was the first child, and the next part of, the part of the magic here involves the fact that we're literally creating a duplicate of the same file we're currently in, and we pick up where we left off. So anything that's happened before that has happened, and everybody's getting a copy of that stuff. So I will know that I'm the left child, or the first child, by our example here. I say the left because this is the first guy we've been spawning off as the one on the left. I know that because I'm doing my logic inside of the first if statement, as opposed to the if statement that's inside of the parent's else. All right? So I'm the first child. I know that my child number is 0. Now, because I'm the first child, I might have to have children of my own. All right, so but we'll pause this for a second because there's no blocking going on here. So my parent spawns off that second child, who gets child number 1, right? Who's going to increment by 1. Okay, so now I'm child ID 0. He's child ID 1. Now it's time for me to spawn off some children. What's their child numbers going to be? How do I guarantee that my child numbers are unique to me? How do I guarantee that I can look at my children and guarantee that they are my children?
Start with the 0, or do whatever.
Tell me more about the do whatever.
So you start. So like you started with a 0, and then it becomes 1 and 2, and then no other one will start with a 0 because it's the parent's number that you're going to take as
So have the child be 0, 1, or 0, 0, 0, or 0, 1.
Okay. Well, what format are you going to store that in? PID is basically a glorified integer, right? Okay. And our child num is as far as I've advertised it here, at least, I haven't put a type in front of it. Looks like an int.
Yeah, if you start doing like 0, 0, or 0, 1, you might need to change that too.
So you could do like, if it's a left child, make it odd, and then add by a certain amount, and if it's right, then it's even. That would
Why don't you just
Yeah.
add a number to the end of it? So if you start off at 1, the first children is
Well, that's
1,
where-
1.
Yeah.
The right
That's
child
what I was-
is 1, 2.
That's
Okay.
what
Down a
I was
level,
thinking.
it's 1, 1, 1, 1, 1, 2, and you go over 1,
that
2,
was
1.
Okay.
1, 2,
So you want to
3.
build up
I
strings.
said that
You
already.
can do an integer or a string or whatever.
I said that.
Like you can do it with an integer. You just have.
Yeah, you'd have to do funky math.
Yeah.
It's
Well,
gonna be
no,
easier.
a little bit. Yeah.
Yeah, so whatever. So it's probably going to be easiest to build a string, but whatever.
Sure.
You know, because at the end of the day, what are we doing? We're writing out to a file.
My question is, why do these processes not know about their own unique ID?
They can. They just the fork command didn't give it to them.
It just seems.
Yeah, there is a function to get your own PID. So I mean that would, but I'm just keeping it exactly what we've introduced, right? So each child is going to have a way of uniquely representing themselves, right? So we can agree that we can MacGyver that unique ID. Okay, if I'm 0, he's 1. My child is going to be 0, 0. His child will be 1, 0. His first child will be 1, 0. My first child will be 0, 0. My second child will be 0, 1. His second child will be 1, 0. Unique, right? All right. So I know you can take different approaches to this, but we can guarantee that each parent knows how to uniquely identify his children. We can come up with our own little secret code. Make sense? All right. So now we're so that's at this level. So this is me right here. This is Joel. We've both looked at our sublists and we've decided, okay, well, we're not sorted either, and we're too lazy to sort ourselves because that's not what the merge sort algorithm says to do. So rather than doing any work ourselves yet, we're going to go ahead and spawn off our own children. Give them unique IDs by updating our child number, whether it's a string or whether it's a number, just making sure that we understand that we might have some doppelgangers out there and we need to avoid that. Okay? So we update our unique child IDs, whatever, and we spawn off 2 children who spawn off 2 children. Now the question is what does the waiting parent do? Whether it's this waiting parent or this waiting parent or this waiting parent, what does a waiting parent do? Nick just spawned off 2 children. He can't do any work until he becomes aware that both of his children have finished their job. And how did we decide we were that I'm gonna be able to notify my parent using only the tools that I have available to me? That I'm done. All right, so I'm gonna write something to a file. Fair enough. All right, so I'm gonna open up a file and I'm going to just append something to the end of the file. Because I definitely don't want to overwrite the file, right? I don't want to be in competition with how many dudes are writing to a file at once here? Potentially. Yeah, a lot. So we need to be careful that we're always appending to the file. What about file locking? We talked last time about one of the, when we're creating a file, one of the flags. We were looking at ocreate. One of them was for locking a file. Okay, but let's say that we don't use that. There's a flag for locking a file. We looked at it in the book. But even if let's say we don't use it, how do we tell? So we're back in the Stone Ages of our operating systems. How is file locking accomplished? I want to make sure when I open a file and I write to it that my parent's going to become aware that that I've made changes, right? I want to make sure that that is something that happens. But at the same time, I happen to know that I have a sibling who's also doing their job, and I want to make sure that we both don't overwrite each other's work. That I don't write in there that I am here's my unique ID. I write it to the file, and then, because of a race condition, because we just asked the question, what's the parent doing? So Nick is constantly opening this file and reading it, opening this file and reading it, opening this file and reading it. So he's using it as read only. That's okay. Right? So he's not running into the problem of overwriting part of the file or something like that himself. But what if he read the file, and immediately after he finished reading the file, I wrote to the file, and right before he reads from the file again, Joel writes to the file. I never was able to get my message to my parent. Does that make sense? Go ahead.
You could have another file that would essentially have left or right in it, and if that file said left and you know you're a left child, then you could write to the file, and then you could change it to right so that the other file knows that it's okay to write to it then. And have the parent change the left or right one.
Okay. How many children does any parent have? Two. In our world, right? Okay. Okay, 2 children. Now, Nick, can you uniquely identify your children? We talked about this a few minutes ago, right? Okay, your left child is 0 if we're at the top level. His right child is 1. So could we, from my perspective, since I know what my ID is, could I write to a file called 0.dat or 0.text, something like that? I could do that, couldn't I? Could he write to a file called 1.dat or 1.text? Now those are completely separate files, right? Completely separate files. And no longer are Joel and I in competition. I don't have to worry about one of us overwriting each other's files.
That's what being siblings
Okay.
is about.
And what's Nick going to do? Nick is just sitting there going through his loop and saying, okay, well, I'm going to read 0.dat. Nothing's there yet. I'm going to read 1.dat. Nothing's there yet. I'm going to read 0.dat. Nothing's there yet. I'm going to read 1. Oh, finally, Joel is done. Well, one of my kids is done, so I'll stop checking 1.dat. I don't need to check him anymore. I'm going to go back. I'll read 0.dat. Nope, 0.dat. Nope, 0.dat. Nope, 0.dat. Ah, finally. Both of my children are done. I can fall out of that busy wait loop. And now I know that I can do my chore. And my chore is to do what? The merge step for a merge sort, correct? That's not bad, right? You create another array that's the same length as end minus begin. And you do your little merge step between those two. Merge everything back together, copy stuff back over. Ah, but wait a minute. What am I copying back over? Because right off the bat, we had this array. And it would be great. We wouldn't have any of these problems, really, if this array was actually shared among all our people, right? But what are we actually going to do? What's that parent looking for? The parent is not looking for the child's ID inside the file. The parent is looking for a file that has that has the child's, the file name that's named after the child's ID that already has the data in it, which is the contents of that array. Maybe 1 element per line, with the very last line maybe saying something like done or something like that. So what the parent's really looking for is the existence of the word done. That lets the parent know that not only has my child finished doing his sorting, he's provided me with his sorted information, 1 element per line, and he's let me know that he's finished. It's that done word that guarantees, I mean, realistically, I don't care if I just picked up the D or the Let's just keep going. Just keep going. Whether all I want to guarantee is I've gotten past all those other numbers, right? I want to make sure, if I'm in Nick's shoes, I want to make sure that the child has already written the entire contents of the portion of the array that he was in charge of to that file before I go and say, okay, well, I can now comfortably read all that stuff back into a local array, an array that I know. Basically, the parent says, I know that my current array isn't that useful. But the good news for me is when we think about the normal implementation of a merge sort, when we do that merge step, don't we create a new array anyways? And then don't we go through that new array and copy the stuff back over into the original array? Well, in our little algorithm here, from this parent's perspective, he doesn't have to overwrite that original array. He's just writing his sorted data to this file. And that original parent is eventually going to read in what? An array, or read in a file of sorted data. And then he's going to merge those two together, and that's his answer. That make sense? So we have to think about this from a MacGyver perspective. Each of those children needs to provide the contents of their partially sorted array. That, every child is only interested in bucket begin to bucket end. Now the parent, Nick, he knew which portion of the array I was interested in. He knew which portion of the array Joel was interested in. Okay, so when he reads from my file, he knows what buckets those numbers correspond to. When he reads from Joel's file, he knows which buckets those values correspond to. Then Nick can do the merge step for his portion of that list, which is going to be his version of begin to his version of end. He'll then write his answers to a file that is whatever his ID is, dot, or whatever we call it, his child number, dot, dat. And that his parent will know where he left off. Now, if we want to be good, good stewards, we probably should go ahead and delete the files after we've read in the files from our children. Otherwise, you're just going to have this directory filled up with hundreds of just weird-looking files that just happen to have partial sorted numbers in it. But the assignment wasn't to leave your directory clean. The assignment was sort the data using the fork command, right? So you don't have to delete them if you don't want to.
You do if you want to do it a second time.
Huh?
Otherwise, you do if you want to run the program more than once, because otherwise.
No, because the children would overwrite the file.
But the parent would immediately see that there's already a file, wouldn't it? Like as soon as it created a child, it would immediately.
You're right. So if you wanted to secure that, what the parent would do is it would immediately open those files and blank them. That way, it wouldn't find done in the file. Okay. So when you hear it like this, is this more doable now?
Okay, but we spent an hour not even doing it. We haven't even started it yet.
Okay, fair enough. So how many lines of code is this actually going to be? You've seen a merge sort before, right? Merge sorts are pretty short, aren't they? And before we ever jump into programming, don't we have to solve the problem first?
Almost no. That's how I do
That
it.
happens.
Yeah. And how did that work out? How did that work out for everybody on this one?
Decent. Better.
Did it sort? Okay. Anybody else get something working? Okay. So how did you end up doing it?
Interprocess communication.
Okay, so you ended up using.
I was trying to figure out a way of doing files, not necessarily like the way we were doing, but trying to figure that out, and I could not figure out a way to have them reliably communicate with. Like my big thing was that one might finish before another one, so this might put a 4 here, this might put a 2 here, or something like that, and then that's wrong. And then me and Austin and Zach were talking about using the wait to wait until, so the parent had to wait until both of its children were done and
Yeah.
stuff like that. But none of it worked out nicely.
I mean, but you still had to do file I/O.
Yes.
Yeah. So I mean, the ideal situation would be wait, but then also have shared memory, so you weren't reading and recreating your local array from files or something like that. So if we're looking at a full solution, that's the more, I guess, more convenient full solution. But not using any inter-process communication, this solution involves, I mean, we have to be a little careful with the merge sort, but isn't merge sort, even with recursion, a little bit tricky? You know, a little bit. I mean, we have to be careful with it that you don't like leave a bucket away, right? So probably the real first play is to write it recursively first, right? Get it working. That way you know all your begins and ends are lining up and all that stuff. And then you're going to say, okay, well, rather than these recursive calls, I'm going to now replace these with forks. That make sense? All right, so for Monday, I'm going to be nice.
Do you know what that word
Do you not want me to be nice?
I do want you to be nice. I'm waiting to hear how nice you're going to be.
Some of you might already be done with the assignment.
Just go savage. Full
Full-
savage.
For Monday, okay, we could all agree. Well, everybody, hopefully you turned in the assignment. You gave me your self-evaluation of what you went through on this. Now, after we explained it today, do we have a new appreciation for MacGyvering?
Yes.
After we went through it, this doesn't seem as bad anymore, right?
It seems pretty terrible. It's just impressive that we figured out that. I would say it is very impressive how much simpler this is than what I thought it would be.
Okay, fair enough, fair enough. So for Monday, everybody write a traditional merge sort in C with recursion. No forking, just using one array. Get a merge sort working. Okay, what's that going to guarantee for us? That's going to stage us for knowing that begins and ends are correct, knowing what the left child will have to deal with, what the right child will have to deal with, right?
So are we still doing our merge sort for our random binary array?
Sure, it doesn't matter. Yeah, I mean, if you want to use binary numbers or just random integers, that's fine, I don't care. Okay, everybody understand? So, just a normal merge sort written in C. And have that working for Monday. Okay, I will see everybody on Monday.